So, hi, I'm Charles. I did this thing called with a friend called Real-Time Vulkan Path Tracer, and we abbreviate to RVPT because those four words get really, really annoying to say over and over again. If you know anything about Vulkan or path tracing, I think the intent should be obvious as to what it does. But for those who don't, path tracing is a rendering technique that is used in movies and animation and CGI. It's very, very pretty. It's also it uses ray tracing where you shoot rays through a scene and you test what the light rays hit, and that's how you get your picture. Path tracing is distinct from ray tracing because it uses Monte Carlo integration. So instead of shooting light rays in a perfect grid, it shoots light rays randomly throughout the scene and then just sums up what it gets. So what isn't path tracing? Well, it's not fast. It is God, very, very slow, relatively speaking, because it can often take 10,000 individual rays per pixel to get a coherent image out of it. It's not hardware accelerated. There is the caveat that there's the NVIDIA RTX and the recent consoles all having ray tracing support. What that is it's part of the path tracing algorithm, but it's not the entire thing. So there's no real hardware acceleration for path tracing. And I mentioned it's not fast, but that's so. Vulkan is a graphics API. It's a successor to OpenGL. It's explicit, it's verbose, it's fast in that you can schedule your GPU access very, very well. And unlike OpenGL, where you were kind of guessing as to what the OpenGL driver was doing, um, it's it's my like I work at a company that does Vulkan full time, so it's my bread and butter. Um, but it is a rasterization based API where 99% of the API is dedicated to dealing with GPU's rasterization pipeline. So fixed function triangles, programmable shaders to with fake lighting methods that rasterization uses rather than real lighting like path tracing. Um, so Vulkan does have the recent RTX extensions that I alluded to earlier, but for our VPT, I didn't use any of that. We just use compute shaders, which allow you to just talk to the GPU hardware and do generic compute tasks. So the big idea for our VPT was just to try to make path tracing happen in a real-time situation. And so our obvious choice was Vulkan because it allowed us the most access to the hardware without having to second guess ourselves. And it's also the new shiny thing that I knew that I could actually do stuff with. Um, I kind of wish I had my other friend who helped me make this. His screen name is Legend, so I call him Legend. And he's the guy who knows path tracing. He's the guy who actually would write the compute shaders, but I'm the guy who wrote the Vulkan parts of it. So all the setup, all the command recording, all the presentation loop shenanigans. So um, it's a community project in that while it's mainly a legend I was working on it, we host it on the graphics programming GitHub account and have had several other people come in and contribute small things like bug fixes to large things like entire new integration algorithms. So Criver is some wizard of ray tracing. He's like, here, I'll just throw in some of the work I do, and it was really awesome of him. Um, so this slide should be near the end because it's like a plug, but I really just want to get it over with so I can start talking about bugs. So the features RVPT has is kind of hackery dashery, where we implemented what was necessary to get started and then just kind of went from there. Um, and the project started out in, I think, late May. Legend asked me if I wanted to work on a project with him and another friend. The other friend wanted to help, but then got bogged down with life and so had to stop and had to go do other things, which I totally understand. Um, so it's mainly been Legend 9. We started with just getting a triangle on the screen, just getting a compute shader to render a triangle on the screen. just getting a basic input handling so you could move the camera forward and backwards, but it really wasn't a camera at the time. It was just a little printf statement saying you moved forward or you moved backward, all that kind of stuff. But over time, we've added more and more things. So stuff like model loading, where we take in a OBJ file, we turn it into a list of vertices, and we throw that at GPU, and now you get a pretty model instead of just random triangles and spheres. We have temporal accumulation, which is a way to make the image prettier without by just sampling over time. So I guess I should open up. I should have started with the demo, but it allows you to use more than a single frame's worth of compute power to get a output image. So it's kind of like blurring, but instead of blurring, you're just taking more and more samples. It's actually exactly like photography with a light exposure. The longer your exposure time, the more light you get, which means you get a brighter image, but it means you get more clarity. So ImGUI is a GUI framework that I've implemented for the project. It's a very common library that you see all over the place, but it's pretty awesome, very easy to use. So there's different integrators. Integrators mean basically rendering algorithms here. So different algorithms that were seminal research papers at one time, but are now ancient history. Sounds like Kaguya rendering is some of the later ones, whereas Witten style ray tracing is from the 80s. And there's different camera modes, so you can change it from a perspective camera mode to an orthographic one. What we have in the works when we have time and energy to work on it is a bounding volume hierarchy acceleration, which is, it makes the thing faster, in short. If you want to know more about what a BVH is, look it up. It's a bit complicated to explain in a two-minute talk, or a 2-minute time frame. Currently, there's no texture support. You can add colors and different material types, like shiny, like diffuse, like a mirror, but not anything beyond those basic characteristics. Temporal reprojection is temporal accumulation on steroids, and it is how you get pretty images in real time rather than having to wait 5 minutes to get a pretty image. PBR materials, that's just saying we want better material support, and eventually we want to be able to do animation, and so we could actually do a semblance of what a game engine could in having a path tracing, but also be real time. Animation itself is kind of complicated, but when you have path tracing in the mix, it gets extremely complicated because the way you make path tracing fast is diametrically opposed to how you make animation fast and usable. So I need to open the project now because, yeah, I wanted to blaze through that. I had slides just to jot out ideas, but I didn't have slides to explain everything in detail. Projects, documents, projects.
I don't know. We are still seeing your LibreOffice.
Well, it's not open yet. I have to find the darn thing. Do I have to build it? I may need to build it. So that's fun. Okay, I have to build it because apparently I didn't have it built before. Most of the work of the project happened a month or two ago or more. So, oh,
We can't see anything.
yeah, it's not building it. Why are you not building it?
No, we can't see your ID or anything.
Oh,
Just Office.
yeah, I see why it broke. Let me. Can you see that moving? Okay, I'm sorry.
Yeah.
Sorry, I had to. What the heck? I have to build it from here? Okay, I thought this was ready. I got home from work and immediately got into the call, so that's why I'm like scrambling. Documents, projects. So this is the compilation screen. Are you kidding? Oh, I need to do from here.
Do you have something already built in your directory, maybe?
I thought I did, but apparently the IDE decided I'm going to delete it. So I'm having to rebuild it, and it's being a bore about everything. So I apologize.
You're good.
Yeah, no worries.
Maybe I have it like just randomly thrown about. Also, Windows builds take forever to set up, so I'm having to wait for that, which is very annoying. So, I mean, I could show you the code while it's building. That there's a heck of a lot. Can you see the code?
Yep.
Okay.
You sure can.
Did it finish building? It may have. Crap. It's trying to do this thing again. Let's try this. So, well, it's okay. Apparently, I can't get GLFW. Does not Mac. Okay, well,
The Windows system is something that just always cause troubles.
it's
SBR is even worse.
well, this is not GLFW's fault. It's just being weird. You get to see me try to debug this. Let's undo that. Then delete everything. And then delete cache and reconfigure. So, okay, it's going to use the Visual Studio build. Oh, and it's found Vulkan. Okay, the proper version.
I thought Vulkan was destroyed in the last movie.
That's Vulkan with a K, not with a C. So we intended to make this usable from the context of a library, but as it stands, it's mostly only usable as an executable. And the real problem is just window handling, because if you want to make a library that can use the GPU arbitrarily, that's not that hard. But if you also want to make it display to the screen, okay, it says it worked. Did it work? Build. Yay! It did work. Yeah. Okay, now I have to move it. Okay. Can I resize it? No, I can't. That was hard to do, so we didn't do it. So this is what path tracing looks like when you're trying to do it real time, and the camera is inverted. There we go. Wait. No, it's still, there we go. So this is a beautiful bunny that we loaded with our model. Currently, it's the only model we have, but that's just because we're lazy, not because we can't. At least I ascribe it to being lazy, not to anything other than that. The temporal accumulation is, as I'm moving the mouse around, you can see that it's very fuzzy. and it's not clear. And I hope compression isn't clearing it, making it harder to see. But once I stop moving the camera, the image starts resolving. And that's because instead of taking 5 samples over the course of 16 milliseconds, it's taking all of the samples from the time I stopped moving the camera until now. So it's, it can do a couple of samples a second every frame. But if you're doing that 60 frames a second, then you're getting hundreds of samples over then thousands and hundreds of thousands over time. But as soon as I move the camera, it stops because the camera, when you move the camera, each pixel knows what it has. The temporal accumulation happens per pixel, but when you move the camera, you change what that pixel represents in the scene. And so if you were to try to accumulate and move the camera, you'd get smears and just artifacts. It wouldn't look right. Temporal reprojection is the idea that you can figure out where that pixel should be after moving the camera. So it would keep the accumulation. It would just move it around every frame. And it has some artifacts on the edges or wherever there's new visual data, like a new depth value, but it's also much, much harder to implement. Temporal accumulation is pretty much just keep track of the last 5 computations and reset if you move the camera. So the ground is not a plane, but a sphere. And if I go far enough away, you can see that it's a sphere. You can just barely make out the bunny in the center. And if I go back, you can see it. And here we go, one again. I mean, it's a sphere. I don't know what else to say. So to show us some of the modes, there is all sorts of different, these are the integrators. So binary means did I hit something or not? So you can see that the rays that are black are the ones going off into the distance, into the sunset. The ones that are white are hitting something, anything. And in this case, it's the shape outline of a bunny. So if we go to the next one, why did you not work? Why are you not working? Okay, well, this color is broken apparently. So, oh, it's not broken. It's because the color is white, but it has a blue tint to it. Okay. And the color is only getting the color out of it. It's not doing any tracing or anything other than the raw color. So the depth value is just how far away from the camera the ray hit something. So if I get up close, it's all white, but if I get further away, it gets grayer and grayer until it's dark. Normals, this is just the direction everything is pointing in. You'll see this is very useful for debugging various aspects. Utah model, wow. Oh, okay, there we go. So the Utah model is basically 1960s era rendering technology or 1970s. So it's effectively solid color shading. Okay, that bunny's really, really far away. I'm gonna do that. Okay. So ambient occlusion. This is, I guess I'm now just explaining random graphics effects instead of anything useful. But ambient occlusion is the measure of how much light some surface gets from the ambient area around it. It's like if you in the corners and edges between walls, it's darker because there's less chance for the light to hit at the corner because it just bounces right out, and it's oblique and hard to get to. So if we get not under the bunny, but not, you can see that it's very dark underneath the bunny here. That's because light has a hard time bouncing in it and illuminating it. So now we're actually getting into the proper ray tracing methods. Arthur Appel is a researcher and developed a rendering algorithm that's, if you notice, solid shading here. So instead of being soft shadows like in real life, it does a single hard ray cast and it detects whether it was in light or not. So in this case, all of the pixels that are underneath the bunny, they're testing whether they can see the sun or not. And if they can't, they're black. If they can, they're white. The next rendering mode is Turner Whitton, who added refraction and glass spheres, so they could have mirrors and balls that have different indexes of refraction, and still using that single point shading for shadows though. I forget what Robert Cook added. I believe that's the
Stochastic.
Stochastic. Thank you. Okay. Yeah, I'm not the person with all this background. I'm actually the you could say the back end engineer who just mungs around with the engines and whacking it with a wrench rather than knowing all the different algorithms. James Kajia, I alluded to earlier, and it's the fancy algorithm that actually does path tracing, if I recall correctly. And then we have this thing, which it's very, very chuggy, getting 15 frames. I don't remember. This is basically just a signed distance field kind of thing, but clamped. Okay, and then we're back to binary. So that's just the list of the different modes. There's different camera modes. So we have perspective is the absolute bog standard one that everyone sees in their daily life. Perspective. A orthographic projection doesn't recede into the distance, so farther things have the same size as near things. This is useful if you're doing CAD work, if you're doing blueprints, if you're doing any sort of physical engineering that you need to preserve spatial relationships on the 2D plane. And then the most fun one is spherical, which maps the 360 degrees around the camera onto a 2D plane. So you can always see everything, and it's very confusing because going left and right doesn't do what you expect. Going forwards and backwards it's a mind trip. So, where's the camera? There's a camera. One fun thing is that you can change which render modes you use at a time to compare them. So you can do swipes like that because that's fun. And that's, and most importantly, you can change the number of bounces. So if you want a infinite mirror, you need to have bounces for as many times as you want the infinite mirror to go, and that would be your max bounces. Your AA is just, oh god, how many samples you do. So I'm doing one sample, and apparently that breaks everything. So let's go to like 3. And that still breaks everything. So I go back to 12. Why is everything broken? Everything is broken, and it's crashing. And so slow. I'm torturing my poor computer. Yeah, there's a reason there's only a single bunny being shown on the screen at a time. Okay, I think it's just better to... Oh god, okay, my entire system was unresponsive. So, I'm gonna add just another sphere at 5. 5. And it's gonna use material dielectric, which is, so it's gonna be 1, and it's gonna be a size of 1 because that's how you do things. You have to rebuild it. So I'm gonna start it. Hopefully this works. Does anyone have any questions? I'm blabbering on, so.
Wait, so you don't have any BRDF? You have like ray tracing and weekend style 3 kind of materials?
So far, yes. We got tired of it because it was a lot of work. Okay, there. I'm not showing the screen. And as it turns out, compute shaders are not a good way to learn ray tracing because there's little to no debugging, and all the nice things that you get in a host programming language you don't get, so you have to either re-implement yourselves or you have to deal with the fact that you can't do recursion or like even basic for loops at times. So is this dielectric? Okay, it is, but it's not very shiny. Eh. Okay. So if I do mirror, what happens? So, I mean, the long-term goal was to be able to make games with this, but we started hitting the reality that that would be very, very hard to make performant and actually usable. Why is it?
Yeah, like from what I heard, even with RTX, which can just be 10 times faster than this by default, you still need to do a lot of work
Yeah.
to
See,
make it
like,
fast enough for games.
yeah, the things that ray tracing helps you do is global illumination and lighting effects that traditional ray tracing cannot do for the life of it without hacks, artifacts, and glitches. And that's great and all, but half the reason path tracing is so powerful is because of the material models that you can use when you have a path trace scene rather than a rasterized one, because you can start doing effects that are kind of that you have to approximate with, you know, with a traditional rate. I don't know. So yeah, we were trying to make games with this, but even with the BVH, you couldn't probably have more than a couple of hundred triangles in the scene at a time, and that's not very fun. Why is this? Oh, I need to do one more. So that should. Oh, that's why. I figured out why. I'm adding two materials, and the material that the sphere was using was the same one as the bunny. Okay, and I need to move it back to where you can see it. Okay. Aha. Okay, now it's a great ball of light. So let me take that to 0 point, just 0. Live coding. How fun. Yeah. Oh. Okay. There we go. Okay, here we go. Here's the mirror. You can see that the bunny. Ooh, where did I go? I can't go in it. The bunny is being reflected off the mirror. Yeah. That's something you couldn't do at all in traditional ray traced games without first either trying to render the scene from the camera's point of view and then rendering from that, or using screen space effects where you just say, okay, the camera can see this part right now, so I'm just gonna copy it and flip it over and put it inside, like on top of the water as a classic screen space reflection effect. So that's why we want to be able to have path tracing, but to do that requires a lot of finagling, because you can see how blurry the image is as I move the camera around, and I know temporal reprojection helps, but it's not perfect. So let me do dielectric. That should be cool. Yeah, this is this is very much technology that is extremely experimental and not very usable. Is this? Yeah, it's a glass sphere. I don't know how well you can tell it, but it's diffracting the, it's not reflecting, it's diffracting the ground around it.
We
can't
can
see
only
it right
see
now.
your.
Oh
your
crap,
score.
you're right. I'm sorry. Here. Uh, why can't you see what I'm seeing? Jeez. Just look over my shoulder. Uh, so maybe it is just still a mirror. I swear I compiled it. Anyways. Huh. Maybe it isn't. Anyways, I thought it was. Yeah, it's still.
It looked like the electric. If you look
Yeah,
carefully from the last angle you look at.
I'm trying to make it so that I can walk inside it because it looks really, really cool. I'm just not sure I'm doing it right. Let me do comma 0, comma 0, comma 1. There are some hacks going on with how we pass data to shaders because, again, compute shaders and you can't pass data easily. So you have to do it in these big arrays or you have to follow alignment rules, and just general GPU programming is wacky. Yeah. I could just actually look at the shader. Okay. So, yeah. The only other thing I have is bugs, pictures of bugs, which are kind of fun to look at. Does anyone have any questions that or things to do with the actual program as it is right now?
What happens if you just walk into that sphere?
What if I do what?
If you just walk into that sphere, what will happen?
It goes black.
Okay, I think you probably get snare law wrong or something. Just like you don't deal with back face, only front face.
Well, that might be. It used to be working. So let me go and find the picture of it working. So like actually, oh, am I chugging? No, I'm not chugging. Okay. I'm actually going to present because there's a video. No, there's videos and I can't show the videos easily without present. Okay, so now, so we took a lot of pictures, bugs, milestones, all the things we could think of that looked pretty. This is the first triangle. You can see the ImGUI is already working on it, but hey, triangles. This is one of the test scenes we had when the only thing that was happening was basic reflection, so like mirror surfaces on spheres, because sphere intersection is easy to understand. So I can't really pause the video, but you can see inside the sphere is a reflection of the sphere you're sitting on and the other spheres in the scene. This is what happens when you get things wrong. We were doing some arithmetic about where to store the pixel because the texture is just a giant 2D grid of pixels and we don't quite know where to store the current pixel. And so, well, obviously we didn't get it quite right here. This was a floating point bug. So the further you moved outwards, it was actually moving inwards, but it was causing floating point errors. And it was very, very crazy. We don't actually know what caused this, but the next iteration fixed it. So we just kind of went with it. Again, I think this is corrupted GPU memory. We don't know exactly what caused this, at least because I wasn't the one who experienced the bug. That was my friend who was currently sleeping. So if he was here, he would probably be able to explain it in detail. Here's a Cornell box. If any of you have ever done graphics like research stuff, you'll have seen Cornell box referenced as a standard sample for displaying various things. So we threw one together quickly to make it show that we can do a Cornell box. And there's a glass sphere in the middle that's refractive and blue, so it illuminates the floor in a nice blue tinge. Here's a video of it. You can see just how bad the the original sampling was. We have 37 samples per pixel, and it's super noisy. So that's something we fixed. And so here's some of the progress pictures. So this is kind of what it was originally. This is like we just took some noise on the CPU and threw it at the GPU and then just used that. But that had terrible coherence numbers, or terrible coherence. So it was very staticky. This is definitely not correct. As you can see, everything's vertical. That's just because we were using the Y value to seed the thing, but all of the Y values were the same per vertical column. So they all got the same sample to use, which means that they all pointed the same direction and caused craziness. Here's a slightly better version of the sampling, but as you can see in the top left corner, it gets wavy and curvy for reasons that have to do with aliasing and number analysis. This is a slightly better version of it, but as you can see, has a nice diagonal symmetry that shouldn't exist. And we finally fixed our problems, and the sampling that you see in the application today is what you see today. This was the first temporal accumulation sample or example we have. If you notice how it's jittering back and forth, that's because there was a bug in how we sampled the temporal accumulation image. Here is the inside of a sphere. If anyone's ever wondered what it looks like, I was trying to recreate it, but I couldn't for whatever reason, and it saddened me. So these are like the infinite bounces you'd get when you have two mirrors lined up inside each other. But because this is the inside of a sphere, it's bouncing inside the sphere itself, causing these patterns. So this is our model loading done. We took a picture when we got that done. And my friend was working on the BVH stuff, and in the process of that, he wrote a little visualization to see the outlines of the different BVHs, which are basically boxes bounding volumes. And so that's that. Is that the last? Nope, that's not. This is what happens when you get the thing wrong. He had infinite recursion and just created lines everywhere when there shouldn't have been. Just several of the fun bugs we've had to deal with along the way. And yeah, that's all I have. I just have questions and a thank you slide at the end. So I'm going to stop presenting.